If you're standing by a river, no matter how calm it seems, the chances are that hundreds or thousands of liters of water are passing by you every second, representing an incredible amount of kinetic energy. You could harness some of this energy by putting a wheel in the water and connecting it to a mill. We've been using water mills for hundreds of years to make flour, textiles, and paper, for example. But we want more of that energy, and we want it to power our homes and our cities. Now, if you put a turbine in the water, you can start making electricity. Hydropower is the most widely harnessed source of renewable electricity globally. It accounts for about 75% of renewable generation in the world. But hydroelectricity can have a big impact on the water, on the things that live in the water and near the water. So what do? Well, today we're talking with Gia Schneider from Natel Energy about a new kind of hydropower built around a new kind of turbine, one they hope is more sustainable, affordable, and resilient. Here on Carbon Copy. Well, thanks for joining us, Gia. I'm excited to talk to you today. Let's start with a deep technical question. Where are you phoning me from?
The San Francisco Bay Area.
Well, I guess that's the price you pay for working on something bold and exciting. Sometimes you find yourself in harsh locations. Okay, tell me about Natel Energy and the solution you're working on.
Yeah. So Natel Energy is a company that we founded. My brother and I actually co-founded the company to focus on sustainable distributed hydropower. Hydropower is one of our longstanding renewable energy sources. At this point, about 2/3 of the world's renewable energy supply comes from hydropower. There's a lot of resource potential in Alberta, something like 11.5 gigawatts of resource that could be unlocked. The challenge really is how to do that sustainably, meeting modern environmental constraints and respect where we want to go in terms of river sustainability, and do that in a way that also brings reliable renewable energy.
So when I think about hydro, I envision big hydroelectric dams with a large reservoir and a significant vertical drop to where the water is released below. Is this an outdated notion? How is your technology different, and how do you overcome the need for these elements?
Yeah. So I absolutely agree that what you just described is what generally would come to mind when you think about hydropower. And it is also true that we have a new way to look at doing hydro. Conventional hydro is an analogy for it would be to think about jumping off of the roof of a building to get to the ground floor. That large dam is basically taking out the energy of water moving across the river, across the slope of the river, all in one big step. And what we do with our technology is we enable walking down the stairs. We can take out energy along the slope of the river in much smaller steps. And by doing so, we can then build projects more quickly, so we can get more reliable renewable energy on the grid faster. And importantly, from an environmental perspective, we can make sure that each of those smaller steps are built to maintain river connectivity, so that we are able to ensure that fish can pass safely, sediment can move, of course, water can move. In some cases, you might even be able to integrate recreational opportunities. Like we're looking at designs that would incorporate, for example, whitewater rapids associated with these smaller steps. And all of that is enabled, this more distributed approach to hydro is enabled by the technology that we have developed, which is a fish-safe turbine designed for these lower drops.
I remember vividly when your team presented this concept to ERA, you talked about something called restoration hydro. What is restoration hydro, and what are all the benefits?
Restoration hydro is our approach to rethinking how we develop hydropower in a river in this distributed approach, that where each element, each node in that distributed project incorporates elements that maintain or improve river connectivity. And so things that are restored, what we think about as the non-power benefits that we get with restoration hydro would be things like ensuring that we have water connectivity in a floodplain. So not just that the water is able to, of course, move upstream, downstream, but that we're able to activate wetlands habitat, activate the floodplain on either side of the river at appropriate times, that we're able to drive groundwater recharge for surface to groundwater, that we're able to create diverse habitat and certainly enable habitat along the river, ensure that there's passage for fish, for sediment. So all of these things we then think about in terms of the objectives of the design of the project, not just the production of reliable, renewable energy. And so it's that holistic approach that we think of as restoration hydro. A practical example would be looking at perhaps an old dam that no longer serves a real purpose and perhaps needs to be removed. And in that case, restoration hydro would mean we go in, we remove that dam, and we replace it with new hydropower, but also with a project that now has restored river connectivity and restored river function. In a degraded stream reach, maybe where we have a river that has been heavily modified and no longer functions in more of its normal state, restoration hydro could mean incorporating other kinds of river restoration activities in addition to new hydro.
Very, very cool. So tell me, I want to take a bit of a step back. How does this reduce greenhouse gas emissions?
So restoration hydro or distributed hydro helps reduce greenhouse gas emissions because we are able to produce electricity from moving water with no emissions of greenhouse gases associated with it. There are no large reservoirs with a distributed approach to hydro, so therefore some of the concerns that you can have with large hydro that might have greenhouse gas emissions associated with the creation of a large reservoir, you don't have that with a distributed approach. And then because we are generating energy from moving water, which itself is, of course, carbon free, that means that the electricity produced is also carbon free. An important additional point, and this is very core to why we were focused on hydropower with our innovations, is that hydropower is it's a predictable source of energy. We can control it because we can control the movement of water in a system, and we can predict what is going to come through the system with respect to water flow. And that allows hydropower to be a resource that can help integrate wind and solar into the grid. And in the context of moving to a zero carbon grid, we really need a full stack of solutions that are carbon free or emissions free. And hydro we think of as being kind of at the foundation, one of those foundational elements at the base of that stack that helps ensure we have a reliable grid that is also carbon free.
There's a lot of interest in distributed energy, and I know this is different from putting solar panels on your rooftop at home, but how does distributed hydro fit into the electricity grid of the future with more distributed energy? Distributed
hydro fits, we think, very naturally into the grid of the future in the sense that, for example, actually, the project that we're working on in Alberta with Bow River Irrigation District is a project where we have looked at opportunities to put solar. Like you can you can take the hybridization story of pairing hydro and wind and solar resources straight to the same project location. So we're looking at projects where you would have a smaller distributed hydro resource. It's connected to a point of interconnection on the grid, and you also might have some room right there to put put in a small solar field, and then you are able to connect that to the same point of interconnection onto the grid. You can then, with a energy management system, manage them as a single virtual power plant, a small virtual power plant, and that then becomes a way to have a more dispatchable total resource at that single point of interconnect if that has value for that part of the grid. What our technology does is it makes it possible to develop smaller, more distributed hydropower resources. And that then fits very nicely into the overall direction of a move across the grid to more distributed resources. Now, obviously, in places where we don't have hydro, there are certain places like the desert Southwest, for example, where there is much less hydro resource. So, of course, hydro will be less of a part of the solution there. But there are a lot of places where people live close to moving water, and our solution now makes it possible to develop that resource to provide local distributed energy.
You talked about something that you called a fish-friendly turbine, or I guess if I live south of the border, I would say fish-friendly turbine. Tell me more about that. Why is it important, and what's key to your innovation that makes it fish-friendly?
So that's an excellent question. The key reason why we focused on designing a fish-friendly, or we call it fish-safe turbine, and the reason we call it fish safe is because we've been able to demonstrate, actually, at this point, 100% safe passage of fish through our megawatt class turbine in the field. And so the reason we focused on designing a fish-friendly, fish-safe turbine is because in order to build distributed hydro at scale, so many distributed hydro plants, but also ensure that those hydro plants are able to operate meeting modern environmental requirements around fish passage. The options you have are, with conventional technology, you can put in a conventional turbine that is not fish friendly and you can screen it. But screens are very expensive. Screens add, in some cases, thousands of dollars a kilowatt to the cost of the project. And so our perspective was, if we can eliminate the need for screening for fish exclusion, then you make it possible to cost effectively develop these projects. And so that's why we designed a fish safe turbine. The turbine design itself, so what makes it fish safe, is the shape of the blade. So in a wind turbine, you see the blades spinning, the air is moving those blades, and that's what then turns to generate electricity. In a hydro turbine, it's the same thing, but it's happening in water. And conventionally, hydro turbine blades are very thin. They're designed to be very thin, they move fast, and as a consequence are relatively not fish friendly. What we realized is that we could design a very thick blade, so a blade that had a very, very thick leading edge, and that thick leading edge acts kind of like an airbag, or what it does is there's a zone that gets created, a pressure zone that's created in front of the blade as the blade moves through that water. And that pressure zone basically deflects fish around the blade. It also deflects debris around the blade. And so that means that's the key innovation that allows us to make a blade or a turbine that is fish safe, but also high performance.
You're based in California, and I understand that your team is working on a project here in Alberta, Canada. Now, before you tell me about that project, tell me how it came about. What drew you and your team to Alberta for the project?
So Alberta has a lot of hydropower resource. I think, as I mentioned earlier, there's something like 11 and a half gigawatts, based on some studies that have been done looking at the resource potential. So, and Canada as a broader whole is known for hydro. Hydro is a really important part of the resource there. So as we were looking for places where we could deploy additional projects, it was a natural place for us to look. In addition, an area that we have been focused on here in the US is looking at opportunities within existing water infrastructure, where you have irrigation canals or existing dams or locks and dams that don't produce energy today, but could be retrofitted with appropriate technology to produce energy in the future. And we've done some projects like that here in the US. And so kind of through that network and connection, we became aware of and got in touch with the folks at Bow River Irrigation District. And they had some sites that were very well suited to this kind of a retrofit development approach. They had an existing irrigation canal with existing drop structures in that canal. And then we reached out to them, and they were interested in looking at developing a project. An important part of moving that project forward was the fact that there was also a good program of support from the government in Alberta to help support getting kind of first of its kind projects going. And that was an important part, as very important part as well of putting together this first project.
I'd love to hear more about the project itself. What does it involve, and what do you hope to achieve?
Yeah, so the project itself, for those who might not be familiar, or if you're not familiar with an irrigation canal, basically irrigation canals to take water out of rivers and then move that water to agricultural land where it is then ultimately used to help grow crops. And in this particular project is in an existing irrigation canal. And one feature that exists within irrigation canals is what are called drop structures. And this is because as the canal moves across the landscape, there's changes in gradient, and there is a need to keep the flow of the water within a certain set of parameters. And to do that at certain times, you'll just have a drop structure that looks like a ramp, could be like a low dam, really depends on the exact nature of it. This particular project, it looks more like a ramp if you were to look at it visually. And so the water kind of comes in at the top of the ramp and then falls down the ramp and then exits into the lower part of the canal. And so our project will basically sit at the point of that ramp, and we'll put a powerhouse. So we'll have water that will come into the powerhouse, generate energy in the turbine, and then exit back into the lower canal. The installed capacity will be about around 850 kilowatts of installed capacity. It'll produce about 2,300 megawatt hours a year. And importantly, this project from a carbon perspective will avoid the emissions of something like 1,400 tons of CO2 equivalent per year.
How much is an outdated facility costing you? Whether you're upgrading your equipment, your building, or finding an alternate power source, the upgrades you do now will lead to long-term savings. With the Energy Savings for Business program, Emissions Reduction Alberta is investing $55 million to keep Alberta's small and medium-sized businesses competitive. ERA will cover up to $250,000 per project that lower your costs and lower your emissions. In a province where skilled trades have the local expertise needed to complete these upgrades, it's an investment in your business and our province. Energy efficiency means more jobs, lower overhead, and a better Alberta for all of us. Find out more about the Energy Savings for Business program at eralberta.ca. What stage are you at right now in the project?
We are pretty advanced in the development process. So we have, at this point, to get a project built, you have to go through the process of getting an agreement in place, in this case with the irrigation district, and then move through permitting so that we have all the approvals to construct and then operate the plant. And then in parallel with the permitting process, there's also a thing called interconnection, which is getting approval to connect the project to the electrical grid. And so interconnection and permitting are the two kind of big time-consuming elements in most project development processes. And so we are about 80% through the permit process. We expect to receive the final permits to be able to go forward to construction later this fall. And then interconnection will probably take until early next year to fully complete. The interconnection process is always one that's if you talk with any developer, interconnection is always fraught with interesting things that evolve in the process or emerge in the process of talking with the entity whichever entity you're interconnecting with. And anyhow, in this case, we're in the stages of moving towards final studies on interconnection. We expect that to complete early next year, and the project should then be connected to the grid in the spring next year.
So once the construction is complete and it's up and running, how will you know if the project is successful?
The fundamental metric of success will be hitting our expected energy generation target on an annual basis for the project. And so, roughly right now, we expect it to generate somewhere around 2,300 2,300 megawatt hours a year. And that's the most important metric for any project at the end of the day is can you produce the amount of energy you expect it to produce, because that directly translates to the revenue from the project. So far, we have installed 2 other projects at this point using the restoration hydro turbine, and those 2 projects have both either met or exceeded the expected energy production in both cases. So we've had excellent performance on the projects operating in the field so far, and we certainly have high expectations of a similar success with this project.
So notwithstanding the success you've had so far with respect to fish safety, will you be monitoring this project with respect to any sort of fish fatalities or fish issues?
So the permits do not have a specific monitoring requirement in them. So at this point, there isn't a formal monitoring plan in place for the project itself. We, in general, absolutely track as part of the operations and maintenance of all plants. We're looking at things like, do you have reported incidences of everything from debris jamming your trash rack to, do we see things that would indicate that there's, poor performance with respect to fish or debris? So absolutely, there is that level of monitoring as part of the basic O&M plan. There is not a specific study requirement on this project to do a specific monitoring for fish. And so that often ends up being site by site, depending on the requirements of the regulatory requirements for each particular site drive any formal monitoring that is then done at the site.
So after this project is complete, what happens next? Can this be replicated at a number of sites across the province of Alberta?
So yes, that is part of our overall plan and focus, is to look at the ability to extend, use this as a demonstration of the restoration hydro turbine in Alberta as a base for then being able to look at developing additional sites and additional projects. One thing that we're definitely very interested in doing, and we've done a lot of this work so far in the US, is to work with the relevant environmental regulatory bodies in Alberta, and also reach out to First Nations to look at the potential for restoration hydro, not just in existing infrastructure, but to look at really tapping into the resource, that 11.5 gigawatts of resource, which really exists mostly in rivers in Alberta. And so this is a very active area of focus for us in the US, where in order to unlock that resource, again, we've put a lot of work into defining how to make fish safe, river connecting distributed hydro. And to do that, we have invested quite heavily in doing a lot of fish testing and work to quantify how you engineer these projects so that you're actually able to deliver the environmental performance that's required. And so a next step for us, beyond looking at additional projects within existing infrastructure in Alberta, would be definitely to reach out to, again, the environmental community, environmental regulators, First Nations, to start to say, here's an opportunity to unlock this resource in a way that's actually very sustainable.
As you were developing this project and working with the Bow River Irrigation District, how did you become aware of ERA?
We became aware of ERA through a consultant that we were working with on the project, and they were, obviously we didn't know directly all of the regulations in Canada for permitting, et cetera, and so we worked with a local consultant to provide advice on how to approach the project, what might be opportunities with respect to either offtake, obviously understand permitting and interconnection, but then also look at opportunities for offtake, look at opportunities for grant support. And so it was through our local consultant on the project.
This is most certainly a bit of a self-serving question, but how important is it for organizations like ERA to provide funding in order to help de-risk the technology innovation initiatives such as Restoration Hydro?
It's critical. I think I don't have to. And that's really, there's no hyperbole in that at all. I think that in order to proving new technology, particularly in energy, it requires buy-in from a fairly often very conservative group of folks, whether utility industry, et cetera. And so there's two things that support from the ERA and similar types of support is really critical to unlock the opportunity. One, of course, is obviously the cost question. We're in early deployment. We've only, at this point, like I said, we've deployed 2 projects. We're not yet at the point where we have hundreds of, tens or hundreds of projects installed. And so the financial support is very helpful in coming down the cost curve as we look to deploy and scale. So that's one element. Almost as important, if not more important than that, is building the ecosystem of and building confidence in the ecosystem. And by this, I mean, the irrigation district, the energy companies, the grid operators, that these new types of resources, whether it's restoration hydro, whether it's solar, wind, et cetera, that these new types of resources are resources that we can actually build, we can operate them, and we can operate them reliably, and they can become, meaningful revenue generating generating assets. And support from the ERA was important as we were putting together the project, was important in helping to put the whole deal together, to have confidence from all the parties, including the irrigation district, to work with us to make this happen.
What are some of the most important things you've learned developing an innovative technology and trying to make this project a reality in Alberta?
I think that it requires a lot of developing a renewable energy technology requires persistence, and it requires a lot of ability to think at a systems level. So persistence is one, just because there's, it's a maybe not as much in wind and solar, but in hydro, somewhat strangely, despite hydro having been around for a long time, innovation in hydro is actually a relatively newer thing. And so when we got started, we were definitely very unique in the hydropower industry. And we were also very unique in the broader industry of renewable energy, where a lot of the innovation and activity is happening, and has been happening in things other than hydropower. So persistence is key, because we frankly had to convince a lot of folks who were fairly skeptical that there was anything new to be done in hydro, that this would work. There's a whole range of questions. So that's one. I think the other approaches, though, which kind of builds off of that, is that you have to have a systems approach. At the end of the day, to get a renewable energy technology from idea to proof to scale deployment requires understanding how a lot of pieces work together. Everything from engineering, supply chain, project development. In project development, there's a whole layer of systems, whether it's interconnection, permits, et cetera. And then another layer on top of that is finance. You have to be able to sell the power. You have to be able to finance the project. And so, to do this, you really have to be able to build a team. And to be clear, it's not me who has done all of this. I very much benefit from having a pretty amazing team that has really helped make this project possible. And that's key. You got to have the right team that's able to break apart all of those elements of that systems problem and tackle them, not necessarily simultaneously, but in the right sequence and sometimes in parallel.
Is there anything I didn't ask you about that you'd want our audience to know?
No, I mean, I think let's see. Nothing that comes to mind immediately, to be honest. I think let me just take a minute. No, I mean, the things I wanted to convey were obviously the new tech, what we're doing, and that I do think there's a real opportunity in Alberta, because particularly for us, so I'm just giving you an ad lib here, more conversational, for context, is that like the opportunity in like the irrigation space is really interesting, but it's really like opening up that, Alberta's in this interesting place where 6% of the capacity in Alberta comes from hydro. But it's I think like under a gigawatt of actual deployed resource right now, but yet there's this pretty substantial resource potential. And the real question, similar to what we face here in the US to unlock like the 65 gigs, is really how do we get to environmentally appropriate tech and approaches that kind of deal with the objections to hydro in the past. So we've already covered that. So.
Maybe that raises another quick question, and if there's not much to say, that's totally fine. But is your team working on any other exciting innovations beyond or in parallel with restoration hydro?
Yeah. So one thing, a couple things to note that we have, in addition to restoration hydro and the restoration hydro turbine, that fit into the overall vision of unlocking distributed hydro at scale, is a software solution that we've developed to provide more accurate forecasts of water flow. And that part grew out of the fact that to be able to design and operate distributed hydro projects at scale, water is your fuel, and so therefore having a good forecast of water is critical. Yet the conventional approach to forecasting water flow is relatively grounded in looking at the past as a predictor of the future, and climate change obviously knocks the foundation out from under that approach. And so what we realized is that there was a really great opportunity to take satellite imagery and machine learning and pair that with weather data to create a more accurate forecast. And so that's a product that we've launched over the last year and a half called Hydro Forecast. And it's actually now being used by about 4.2 gigawatts of hydropower operators to inform hydro operations, both in the US and in Europe. And it's a product which we bundle with the controls that go with our turbines, but also is one that can be just deployed on a standalone basis for anyone who's got a hydro or frankly a water resource where having a better water forecast would be important. And I think the thing that we're starting to spend more time digging into is a point I referenced earlier about hybridization. So in particular, distributed hydro paired with batteries has a really great charge discharge profile for maximizing the economic use of battery material, because charge discharge has a big impact on battery life, basically. And so there's some really interesting things there in terms of building hybrid systems for certain markets where that has good value for building that, where we see a real opportunity. And this is less like innovation that we're doing, it's more putting pieces together into a power systems package that makes a lot of sense.
Well, thank you, Gia, both for your time today and also for the opportunity to be part of this exciting project.
Well, thank you. Like I said earlier, the support from the ERA is critical in several ways in this, and we're pretty excited to get this thing built, get the project built, and so that you can then drive out and take a look at it next spring.